Okay, welcome everyone to this week's online causal inference seminar. This week we have Professor Ruoqi Yu from UIUC giving a talk to us about how to learn more from observational factorial studies. Today we have two discussants, José Zubizarreta from Harvard University and Ruoqi Yu from University of Pennsylvania. So the format today is similar to the usual, but as we have two discussants, we also wanted to open the seminar at the end a bit more to some conversations. Without further ado, actually, I should ask Ying if you want to add anything about the Q&A.
Sure. Thank you, Qingyuan. Just some usual things, please. If you have questions, please submit your questions through the Q&A section using the button at the bottom of the Zoom window. And please do submit through the Q&A for us to track it. If you have other questions, you can also, some questions unrelated to the talk, you can use the chat to talk to us. And yeah, without further ado, please feel free to take over, Ruoqi.
Let me just share my screen. So thanks, Qingyuan, for the kind introductions. Thanks all the organizing committee for having me. I'm glad to have this opportunity to share my recent work and discuss how to learn more from observational factorial studies. And the main paper I'm going to discuss today is titled Balancing Weights for Causal Inference in Observational Factorial Studies. And this is a joint work with Peng Ding from UC Berkeley. I'm very glad that Peng is also be able to join us for the online seminar today. So welcome, Peng. And by the way, our paper just became available on arXiv today. So lucky day for us. If you're interested in our work, feel free to check our paper online. So I have been talking about observational factorial studies. It might be your first time to hear this terminology, but why do we care about this? It's actually occurred much more common than we thought in our daily life. For example, many of you may have seen the news in February about the train crash in Ohio, and the resulted chemical leakages have caused severe concerns from the residents living in that neighborhood. Even if our life may not be affected by that particular accident by living in other states, however, we should still worry about the effects of chemical exposures to our health because it happens more common than that particular accident. For example, we might be exposed to volatile organic compounds through both common indoor and outdoor activities, such as home cleaning products, like building materials, cigarette smoking, gasoline, and industrial emissions. It has been shown that exposure to these VOCs can increase the risk of adverse health outcomes such as asthma and respiratory complications, pulmonary dysfunction, and birth defects. The existing literature has been mainly focused on examining one chemical at a time. But in practice, we are usually exposed to multiple chemicals or chemical mixtures, not individual ones. Examining them one at a time can unnecessarily limit our understanding on how one factor can affect the other. Therefore, to close this gap, today we're going to look at 4 common VOC exposures and evaluate their effects on tachycardia for women at reproductive age. Specifically, we're going to consider 4 factors on whether the blood concentration of benzene, ethylbenzene, 1,4-dichlorobenzene, and MTBE exceeds their detection limits or not. These 4 binary factors gives us 16 treatment combinations, and our outcome of interest is heart rate, which can indicate any sign of tachycardia. To evaluate the effects of these 4 factors and their interactions, Ideally, we would like to use a full randomized factorial experiment, which involves random assignment of all possible treatment combinations to units. In doing so, there will be no systematic differences in any aspects among the treatment combination groups, both observed and unobserved. And then we can just measure the factorial effects by comparing the average heart rates in different groups. However, this option is neither practical nor ethical to us due to the potential harmful effects of VOC exposures. As a result, we can only use non-randomized observational studies to evaluate the factorial effects that we're interested in. And in this study, we used the biomonitoring data from the National Health and Nutritional Examination Survey in 2003 to 2012. This gives us 2003 women at reproductive age. And we also have access to their demographic information, medical history, alcohol consumption, and smoking status. It's nice that this enhanced data set can provide us very rich information about the representative sample of the US population. However, we should be careful while working with an observational study like this one, because the treatment assignment is not random anymore. And due to this non-random treatment assignment mechanism, the covariate distributions can be very different across the treatment combination groups. For example, in this table, I illustrate the covariate means across the 16 treatment combination groups. And you can see that they can actually vary a lot. For instance, the proportion of current smokers can differ by more than 70%. So if we observe some difference in the average heart rates between two groups, then we don't know whether this difference is due to different smoking status or is due to the different treatment combination they received. As a result, to draw more reliable causal conclusions, we need to reduce the bias in the estimated factorial effects by removing the confounding effects. And to achieve this goal, one way is from the design perspective. Specifically, investigators should design their observational studies carefully to replicate a randomized factorial experiment as close as possible. And today we're going to use weighting as a helpful tool. So what is weighting and how can it help us? To be more concrete, let's first consider a simple toy example with one binary treatment and one binary covariate. In the upper panel, you can see that in the treated group, there are more individuals with covariate value 0, and in the control group, there are more individuals with covariate value 1. And by assigning each individual a new weight, we can achieve the same distribution of X in the weighted treated and control groups. But which weights should we use to achieve the same distribution of covariate? The majority of the weighting literature has been focusing on the case with one binary treatment, and the most famous weighting method is called inverse probability weighting. As its name suggests, it assigns each sample a weight as a corresponding inverse probability of receiving the treatment. It has been shown that if we know the true propensity score, which is the true probability of receiving the treatment given covariates, and then inverse probability weighting can entirely remove the bias in the treatment effects estimation. However, in practice, we usually don't have this information, so we need to estimate the propensity score. As a result, we might face problems such as large biases caused by propensity score model misspecification and unstable estimates caused by the extreme values of the estimated propensity scores. And to overcome these limitations, in recent years, researchers have proposed a new class of weighting methods called balancing weights, which choose weights by directly comparing some pre-specified basis functions of covariates between the treatment groups. And it has been shown that balancing weights can be more robust and stable than the traditional inverse probability weighting methods under some mild regularity conditions. So can we directly generalize these nice balancing weights to deal with multiple factors? A simple and the intuitive way to deal with multiple factors is to view the treatment combinations as a single treatment with multiple levels. Then we just need to balance the covariate distribution of all treatment combination groups. If we want to follow this route, then we can utilize the existing literature regarding a multivariate treatment, where researchers have proposed propensity score-based methods and balancing weighting methods. This idea of working with a multivariate treatment works well if the number of treatments is relatively small, and it can help us estimate all factorial effects, including the high-order interactions. However, challenges do arise if we have a large number of factors. Specifically, as you can observe, the number of treatment combinations grow exponentially as the number of factors. So if we have a large number of factors, then we need to balance the covariate distribution in an enormous number of treatment combination groups, which can be very computationally intensive. For example, if we have 10 binary treatments, then we need to balance the covariate distribution of more than 1,000 groups, which is a lot. In addition, if we have many treatment combination groups, it's very likely that some of them are rare or simply empty just by chance in the observed data set, making it challenging or simply impossible to balance all treatment combination groups. Therefore, if we have the case that estimating all factorial effects is impossible, can we think about a simpler question? Can we still draw reliable inferences for the relatively important ones? To answer this question, we need to first determine which factorial effects to estimate. And for that, we can follow some key principles of factorial design. In general, researchers believe that lower order effects are more important than higher order effects, because higher order effects are usually believed to be smaller and harder to be interpreted. And this is known as the effect hierarchy principle and is widely accepted in factorial design. In addition, factorial design usually obeys the effect sparsity principle, suggesting that only a small number of relatively important ones are present. And based on these principles, you can see that it's reasonable for us to assume that the higher order interactions are negligible, and we're only interested in estimating the main effects and some low order interactions, say up to order k prime. So in this case, how can we design an observational study for this aim? And today we're going to introduce a new weighting method tailored for the observational factorial studies. So let's suppose we have k binary factors z1 to zk, and this gives us 2 to the power of k possible treatment combinations. And throughout this talk, we're going to follow the potential outcome framework for factorial designs proposed by Discussant et al. In 2015. Specifically, we're going to use YZ to denote the potential outcome if assigned to treatment combination Z. And we're also going to assume suitable. And under this potential outcome framework, any factorial effect of interest can be written as a linear contrast of the expected potential outcomes. For example, the main effect of factor zk compares the average expected potential outcome of receiving treatment zk to that of not receiving treatment zk, uniformly average all treatment combinations of the other factors. Therefore, its corresponding contrast vector has half +1 and half -1, indicating whether the treatment combination Z has treatment ZK +1 or -1. And similarly, we can define the contrast vector of the interacting effects as element-wise product of the main effect contrast vectors. And to estimate the factorial effects of interest, we're going to utilize and observe data with n individuals including NZ individuals with treatment combination Z. For each individual, we observe a triple. A k-dimensional received factor Zi, a d-dimensional covariate Xi, and the outcome of interest Yi. So for each individual, it has 2 to the power of k potential outcomes, but we can only observe the one of them depending on the received treatment combination. And under suitable, we can write the observed outcome as a linear combination of all expected potential outcomes. So how should we use this observed sample to estimate the factorial effects simultaneously? To answer this question, we are going to first consider each single factorial effect tau with a contrast vector G, and then we are going to put everything together. So similar as dealing with one treatment, you can see that we can decompose the factorial effect tau into 2 parts, the average expected potential outcome in the positive part and the average expected potential outcome in the negative part, which we denote by tau plus and tau minus respectively. The problem is that it's not easy to estimate tau plus and tau minus because we cannot observe individuals with outcome YZ and the population sampling distribution F. Because we can only observe individuals with outcome YZ and sampling distribution FC, an easy fix to this problem is to introduce another term, WZ, such that the weighted distribution WZ FC equals to the population sampling distribution F. In other words, our ideal weights can be defined as a ratio between these 2 densities. And this suggests us this sample analog of our contrast of our factorial effect. And here, this weights Wi are the normalized weights depending on the received treatment, and the indicators AI plus and AI minus represent whether individual I contributes to the positive part or negative part of contrast G. So how should we find the ways to obtain an unbiased estimator of tau? We first consider a simpler outcome model that separates the effects of the covariates and the treatments. As you can see, since both mu(xi) and mu z can be written as a linear combination of some basis functions, we call it a generalized additive outcome model. And due to our key assumption that the higher order interactions are negligible, so we assume that the conditional expected potential outcome only depending on the treatment combination through this interaction up to order k prime. Under this generalized additive outcome model, you can see that it's important for us to balance the covariate basis functions. And if k equals to 1, that is, we only have one factor, this is exactly the same as the traditional balancing weighting methods. However, in the presence of multiple treatments, balancing the covariates themselves are not sufficient to give us unbiased estimates. So let's just think about this simple example that say we want to estimate the main effect of Z1. And then by looking at these 2 groups that Z1 has treated and Z1 has control, not only the covariate distributions are different, distributions of other treatments, Z2, Z3, and so on, are also different. And this can also confound our estimated factorial effects. Therefore, it's important for us to also include the factors as additional covariates for balancing, and this will give us this additional set of balancing constraints. As you can see from the form of the balancing constraints, we only need to balance the treatment combinations up to order k prime. Again, this is due to our key assumption that higher order interactions are negligible. And as a result, the number of constraints increases as K prime increases. And in the special case that, again, with a simple factor, this is equivalent to balancing a constant covariance. So it is automatically satisfied, and we don't need to add it as additional constraints. The generalized active outcome model is pretty general because we allow flexible form of the basis functions, but it's still restricted in the sense that we do separate the effects of covariates and the treatments. But in many applications, these two effects can interact with each other. Therefore, to allow this interaction, we discuss a more general class of outcome model by allowing the coefficient of the covariate basis functions to depend on the treatment combination Z. And due to this flexible model, we now need to balance the interaction of the treatment combinations and the covariates. So the key idea is that we're going to view the product of the covariate basis functions and the treatment basis functions as new basis functions that we need to balance under the heterogeneous treatment effects model. As a result, that will give us this new set of balancing constraints. Note that if we do have the assumption that all high-order interactions are non-negligible, so everything matters, and then this set of balancing constraints will be equivalent to balance the covariate distribution of all to the power of K treatment combinations. The advantage of our formulation is that if K prime is less than K, we will end up with fewer constraints, which gives us an easier problem to solve. And up to now, our discussion has been focusing on estimating each single factorial effect tail. As we mentioned at the beginning, our goal is to simultaneously estimate multiple factorial effects. And to do that, we can just apply the previous derivations to each contrast. And that will give us the complete list of balancing constraints for unbiased estimates of all non-negligible factorial effects. And we have shown that under some mild regularity conditions, such a set of weights exists with a high probability as long as the sample size is large enough. But what if there are multiple such choices? Which one should we choose? In that case, we can adopt a common technique in the balancing weighting literature and introduce another convex measure of the weights, MWI, such that the smaller the total of the MWI, the better. For example, Helmholtz used Mx equals to x log x in atropine balancing weights, and Chen et al. Uses convex distance between the weights and the uniform weights to avoid extreme weights in their calibration weighting method. And José or Discussant and his collaborators chooses Mx as x squared in the stable weights. So in practice, researchers can choose this M based on their need and their preferences. But with whatever choices you decide to use, we can formulate everything into an optimization problem, such that we want to minimize the total of xi subject to the balancing constraints that can ensure unbiased estimates and also the non-activity constraints for the weights. And this optimization problem is a convex optimization problem. And to further improve its computation efficiency, we can work with the still form, which is an unconstrained concave maximization problem. And basically here, you can think of this lambdas as Lagrange multipliers of the balancing constraints and gammas as the Lagrange multipliers of the non-negativity constraints for the weights. So if our dual problem has optimal solution, lambda hat and gamma hat, and then we can have this very clean form of the factorial weights that we're going to use. So how well does our weighting estimator work? We have shown in the next part of discussion, we will show some theoretical properties of our weighting estimator with a particular choice of m, such that mx equals to x squared. With this particular choice, we have shown that our weighting estimator is usually consistent, and it also follows a normal distribution asymptotically. In addition, this asymptotic variance, depending on two parts, the variance from the projection of the potential outcomes to the covariate space, and the variance from the residues of the projection. And it's important to note here that although this theorem focuses on a particular choice of m, in general, we do have these nice properties as long as your m choices is strictly convex and also continuously differentiable. The only difference is that the variance from the residuals will differ a little bit. And to further conduct inference, we also propose a consistent variance estimator motivated by Chen et al. Although you both may feel stunning because we do have a complicated form of this variance estimator, but I guarantee you it's very easy to calculate because all these terms we need are already derived in the process of finding the weights. Okay, so that's the first part of the methodological part, and then I just want to pause here to see whether you have any questions.
Yes, there are a few questions, but Peng is doing a great job in answering them, so I think we're good to continue.
Okay, so then we can move on to the next part.
Thanks.
Thank you, Ying. And so, as you can see, up to now, our discussion has been focusing on the case and how to use our weighting method to replicate a full factorial design. And this is applicable if we can observe all the treatment combinations. As we mentioned at the very beginning, a common practical concern is that if we have many factors, and then it's likely that some of them are not observed just by chance. So in that case, we can extend our weighting method to also replicate a fractional factorial design and an incomplete factorial design. We're going to start our discussion with a simpler case to replicate a fractional factorial design. Specifically, a 2 to k minus r fractional factorial design starts with a full factorial design for k minus r factors. And then we're just going to fill in the contrast vectors for the main effects of the remaining factors according to some generators. If we choose the generators carefully, then we can successfully end up with only using the observed treatment combinations, which successfully overcome this issue. The problem is that a 2 to k minus r fractional factorial design only uses 2 to k minus r treatment combinations, even if we observe more. So we do sacrifice our sample size a lot. For example, if we have, say, 3 binary factors, and then we will end up with 8 treatment combinations in total. If one of them is not observed, and then the best we can do is to replicate a 2 to 3 minus 1 fractional factorial design, which only use 4 treatment combination groups. As a result, there will be 3 treatment combination groups that we have observation, but we never use anything about them. And to overcome this limitation, a more flexible approach to utilize all observations is to replicate an incomplete factorial design. And our key idea is to first utilize the one-to-one correspondence between the factorial effects and the expected potential outcomes to infer the unobserved treatment combinations using the observed ones. And then we can redefine the contrast as weighted linear combinations of the expected potential outcomes. And to be more concrete, let's consider this toy example, again with 3 binary factors. Let's suppose that there's one treatment combination that Z8 with all active status for 3 treatments is not observed. So in that case, if we don't, if all higher order interactions are non-negligible, then there's nothing we can do. But if we observe the third order interaction is negligible, then by using this information, we can rewrite the expected potential outcome for Z8 as a linear combination of the expected potential outcome for the other 7 treatment combinations. And by using this relationship, we can get a revised definition of, say, the main effects. And now you can see that the definition of the main effects only depends on the 7 observed treatment combinations. The difference here is just that now for each contrast vector, we don't have half plus 1, half minus 1 anymore. Because of this redefinition, the contrast interest can be 0, can be other values. It now represents how much the treatment combination contributes to the particular contrast. Okay. So in general, this is the one-to-one correspondence between the factorial effects and the expected potential outcomes that we are going to use. So for notational convenience, we're going to rearrange the orders of Z based on depending on whether the treatment combination is observed or not, and also depends on whether the factorial effect is negligible or not. So by using the higher order interactions are negligible assumption, we can have this linear system that we can solve. And this linear system, and from this linear system, you can see that as long as this matrix GUU has full row rank, and then we can have this, we can infer the expected potential outcome of the unobserved treatment combinations using the observed ones. And by substitute this, the previous relationship into our original definition, we can get the revised definition of all non-negligible factorial effects. Again, the key difference comparing with full factorial design is that in a full factorial design, all the treatment combination groups contribute equally to each contrast. But in an incomplete factorial design, as you can see from our toy example previously, the contrasts are weighted linear combinations, and different treatment combinations can contribute to the factorial effects with various weights. And with this revised definition, when we're trying to find the weights, we can formulate the optimization problem in a similar way as before. The only difference comes to the meaning of the previous indicators AI, which now represent how much weights unit I contributes to the positive or negative part of factorial effect tau. So that's all about the methodological part. And next, let's move on to look at some numerical studies to evaluate the performance of our new weighting method. For illustration purpose, we do consider a very simple setting of the simulations. And if you look at our manuscript on arXiv, we do have more complicated simulation settings. Okay, but still for now, we consider the case with 5 covariates and 3 binary factors. And here we suppose that only the main effects are non-negligible. We also consider 3 outcome models where Y1 is additive, Y2 is heterogeneous, and Y3 is misspecified. And here by misspecified, we mean that when we're trying to find the weight, we're going to choose the basis function for the covariates as x1 to x5. So since in Y3, it does contain terms like a sign or the maximum, so it doesn't belong to the basis function space that we consider. So in the first table, you can see that we compare 4 candidate methods. The first one is a simple unadjusted one that we just compare the averages in the positive parts and negative part in the 2 contrasts. And the second estimator uses coefficient in the regression model. And we also consider 2 versions of our weighting estimator. The first one using the balancing constraints from the generalized additive outcome model, and the second one using the balancing constraints from the heterogeneous treatment effects model. We will also vary the sample size from 1,000 to 2,000. And we evaluated the performance using 2 measures, the bias and root mean square error across 1,000 replications. From the first table, you can see that if the outcome is additive, and then all 3 adjusted methods have similar performance, and then they are much better than the unadjusted one. And if the outcome is heterogeneous, and then our weighting method with more relaxed balancing constraints can achieve the smallest root mean square error in all cases. And finally, our method also performs pretty well, even if the basis functions are not correctly specified. In the second set of simulation setting, we're going to evaluate the performance of our new consistent variance estimator. So in the third column, we demonstrate the variance through 1,000 replications in the simulations. And in the fourth column is the average of our consistent variance estimators. We also show the variance between these 2, the ratio between these 2 variance, and also the corresponding 95% confidence interval coverage rates. From this table, you can see that the variance ratio are pretty close to 1, and the confidence interval coverage is pretty close to 95%. I mean, even in the misspecified case, the coverage rate is not very bad. And our last set of simulation setting is actually motivated by our real study, because our outcome is heart rate, which can be heteroscedastic. So we do consider simulations with different levels of heteroscedasticity. You can see that in both cases, our weighting method can work pretty well. The coverage rate of the confidence intervals are close to 95%. And finally, let's return to our enhanced study, which is our motivating example, and see whether we need to worry about VOC exposures. So motivated by the literature, we'll assume that only the main effects and 2-way interactions are non-negligible. So that gives us 4 main effects and 6 2-way interactions, so 10 contrasts in total. And while we are trying to find the weights, we use the balancing constraints from the heterogeneous treatment effects model, and we just use the covariate basis functions as the covariates themselves. And you can see from this figure that our weighting methods can successfully reduce before weighting large standardized mean difference to some level close to 0. And this can definitely give us more confidence about our causal conclusion in the next slide. So here we summarize all of our outcome analysis in this table. You can see there are 2 main takeaway messages. The first one is we should worry about VOC exposure, because one for dichlorobenzene and MTBE can significantly increase our heart rates. On the other hand, it also releases our concern about the existing literature, because in our study, when we consider all the 2-way interactions, they are not significant. And finally, let me just wrap up everything. So today we discuss a new weighting method tailored for multiple factors. We first discuss how to use our weighting method to replicate a full factorial design. And this method is applicable if all treatment combinations are observed. In addition, we also discuss how to generalize our weighting method to replicate a fractional factorial design and an incomplete factorial design. And this is especially helpful if some treatment combinations are not observed. There are two main sentences I hope you can remember from today's talk. The first thing is that if we assume that high-order interactions are negligible, then we don't need to balance the covariate distributions of all treatment combination groups, and we do end up with an easier problem to solve. In addition, if we have multiple treatments, balancing the covariates are not enough. We also need to consider the treatment combinations as additional covariates for balancing. And that's all. Thank you all for your attention. I'm happy to take questions, and I'm happy to hear what Luke and Jose think about this work.
Great. Thank you, Ruoqi, for the great talk. We have received a bunch of questions, but all of them have been greatly addressed by Peng. So I think it's a great time to start the discussion. Jose, please feel free to get started.
Thank you very much, Ying. Thank you very much for having me. It's an honor to be in this seminar and to comment on this very interesting and good work. This is a kind of work that I like a lot. It's what in football parlance, in soccer parlance, can be called box-to-box research, doing theory, methods, and ultimately doing work that is relevant for practice. This work explores, I think, a natural and important frontier, this one of integrating the more traditional literature and experimental design with the more contemporary one of observational study approaches, specifically using weighting. And in this short discussion, I'd like to provide some remarks and perhaps offer some future directions. My remarks are conceptual, terminological, and lastly practical. In terms of concepts, something that I appreciated a lot from Ruoqi's presentation is this emphasis on, in observational studies, designing them and approximating as closely as possible, she said, this template randomized experiment, here a factorial one. And I think that the methods she proposed, they have a lot of traction towards very specifically approximating that experiment. I think that other methods don't do it that closely, even though we also invoke these kind of concepts. Something that I thought was clearer in the paper than in the presentation was this separation between the theoretical construct of the inverse propensity score from the actual estimation procedure. I find that sometimes we conflate the two things, and something that in the paper is very clear is that via this balancing approach, we're ultimately estimating the inverse propensity score weights, but directly, as opposed to in this two-step fashion where we first predict, then we invert. And that usually gets us into trouble. So to me, that's part of the appeal of this weighting approach that Ruoqi discussed. My next comment is it's about terminology. Throughout the paper, this class of weights are called balancing weights, but one aspect of these weights is that they directly balance covariates to control bias. But another one is that they explicitly restrain the dispersion of the weights. And both are relevant, one to control bias, the other one for variance. This is important because we could in principle find balancing weights by solving a feasibility problem, doing nothing with the dispersion of the weights. But here we are actively doing that. And I think that distinction is important. And then there are a number of choices that Ruoqi and Peng did in their work, which I want to highlight. They're often, I think, overlooked from the standpoint of current asymptotic analysis, but I believe they are relevant for practice. First of all is that they started positing a constrained optimization problem as opposed to the relaxed version via the dual. Ultimately, they solved that, but I like that they start from the constrained one. I believe that's important for practice because that allows us to have more traction on the data as we do the covariate adjustments. I think it's important for the practitioner to get an infeasibility guarantee, an infeasibility label when doing the covariate adjustments, so that the practitioner knows whether certain forms of adjustment are feasible or not with the data at hand. And once we know that, then we can know whether we relax the adjustments, we implicitly pose a stronger model or not. But I think that comes more naturally from the constrained version of the problem than the unconstrained one. Second, another choice Ruoqi and Peng did was this one of exact balance as opposed to approximate balance. This is an interesting choice. It makes the problem more tractable, both mathematically and also from a computational standpoint to do exact balance. Nonetheless, in settings like these ones, where the data is ultimately very sparse, this also happens in longitudinal studies of treatment effects with time-varying treatments, balancing exactly for everything is very difficult, okay? And here, approximate balance, I believe, can play an important role. Nonetheless, yes, the choice of the parameter delta for the degree of imbalance, it's an important question and a difficult one. Finally, I wish to highlight that they went for interpolated adjustments as opposed to extrapolated adjustments stemming from non-negative weights. I believe Keele will comment more on this in his comments. Now, as future directions, one question that I had was, what is the connection between the proposed approach to what would be done in the context of linear regression adjustments? In a paper with Ambareesh Chattopadhyay, we comment on the adjustments of linear regression with multivalue treatments, and there may be some interesting connections. The second one is the idea of having exact balance, but where are we centering the samples after balance? This has to do with the target population, namely what is the implied target population of the adjustments. And here I believe the notion of covariate profile can be relevant. Something that I missed in the paper was more of a discussion about multiple comparisons and simultaneous inferences, given the many contrasts we have here. And two possible future directions would be to study multiple robustness, perhaps in the context of the minimax framework by Hirschberg and Bagger. And also a natural question is how to conduct sensitivity analysis in these observational factorial designs. So those are some comments. As usual, I have to thank the agencies that are supporting our work. So thank you a lot for having me.
Thank you, Jose, for the great discussion. Luke, yeah, feel free to take over.
Luke, you're muted if you're speaking.
You unmute myself. There. Okay, now I've unmuted and I can start. Sorry about that. So I want to talk about two issues that are actually on the exact same paragraph on page 12 that, especially when you think about the larger balancing weights literature, raise them. So they're issues that are, to me, just a little buried, and maybe have a little conversation about them. One is about hyperparameters, one's about negative weights. So in the paper, there's this m dot function, which is briefly discussed as a particular kind of model function. And they talk about a couple other choices that are in the literature for this particular function, and then they, of course, mention their choice. But really what's buried in there, because Jose mentioned that, right, that we're typically, in one of the key features of balancing weights is we're targeting both balance and dispersion of the weights, or the variance of the weights, which is really what is a key, I would say maybe the key part of balancing weights versus IP weights, and is really actually rolled up into this function. Just to give you a really quick example. So this is an objective function from a paper using a different kind of balancing weights in a really standard sort of case. This, we're minimizing, right? The weights is this delta term here. This is a balance constraint essentially across treated control distributions. This is that, so that's the bias part of the function. This here is essentially the variance of the weights. And notice there's this little tricky term in there called lambda. That's the hyperparameter, right? Which is controlling the trade-off between the variance of the weights and the bias reduction, right? Because what happens if we only focus on bias reduction, the weights can become quite large, they get too dispersed. And this little term here, lambda, controls that, because if it's 0, then we only focus on bias, and when it's non-negative, we're doing some trade-off there. This is another quick figure from a paper of ours where you can set that hyperparameter, and you get this y-axis here is the amount of bias reduction across all the covariates, and the x-axis here is the effective sample size, and these are hyperparameter values, right? When we set the hyperparameter value to 0, we get a very small the smallest effective sample size, but we do the highest in terms of bias reduction. And then along this curve, as you change that hyperparameter, that changes. What to me was interesting in the paper is that they're doing that, but there was almost no discussion about how that particular choice of their model, because there's stuff in the literature about how to make that choice. That is, you might explicitly make that choice in a data-driven way. You might do it based on substantive reasons. You're not looking at the outcome. Just to me, I'd like a little more discussion of this, at least in this conversation, about how the particular choice, that model class that they chose, is making this choice for us, or is making a specific choice about that bias variance trade-off. But there wasn't, to me, a whole lot of discussion about that in the paper. It also says in that exact same paragraph that they rule out negative weights as a convenience, which I was a little interested in. It seemed to be some of a requirement. Typically, also in the balancing weights literature, right? Negative weights allow extrapolation beyond the data, right? If you, by making the weights by restricting them to be positive, you're preventing extrapolation. If you allow them to be negative, you can extrapolate. It strikes me that extrapolation would be pretty easy to happen, right? This sort of with these, especially when K is large. And to me, it's not just strictly speaking convenience. It dictates sort of what we think about we're allowing the optimization problem to do. So I was a little confused by that phrase, and maybe a little discussion about how they see that in this case in terms of extrapolation. Those are my comments.
Ruoqi, do you want to respond to any comment in Jose and Luke's discussion?
Thanks, Jose and Luke, for the helpful comments and suggestions. I'll just respond them by topics. So the first one I'm thinking about, I think the part you both mentioned is about the bias variance trade-off. I think the parts mainly is just, so for the construction of the exact balance, then we can ensure it's unbiased. But for the variance, I think there are, like in the literature, people make different choices. I think in one of Jose's paper, I think they choose mx equals to x squared by saying like minimizing that will be equivalent to minimizing the variance under when the treatment effect is homogeneous or something like that. And I think for us, when we're doing this analysis, we do found that these M choices will affect the asymptotic variance in the term of the residual variance. But that we also thought about whether we should just like based on that asymptotic variance term, we will just find the M that minimize that term. But then it turns out that I think that will be actually the data-driven choice. It will depending on the specific data set. So for a different study, a different optimal choice of M will present. So that is actually why we're just saying, okay, then the users can choose M based on their needs. So we give, I agree, it's a very coarse description. We didn't give detailed instruction on how to choose that. But I agree. I think we can achieve the optimal bias variance trade-off by trying to focusing on the term of the variance from the residuals. Probably we can just say, okay, for each data set, you can follow a procedure and then find the optimal choice of M for your data set, for your particular study. And then that will be more practical. And for the other topic that I think José mentioned is about the target population. I think when we're trying to construct this balancing constraints, we do have the we try to have make the distribution in the positive contrast part and the negative part of the contrast to equal to the entire population. So we'll assume that the observational study as a whole is representative from the whole population. So that's why, I think our target population will be the population from the entire study. And for the extrapolation of the weights, I would say, while I was working on this, I was actually surprised to see that most papers do allow both negative weights and positive weights. Because at first I would think intuitively, it's very easy to imagine, okay, somebody counts for 2 people. But on the other hand, what does it mean if somebody counts for -1 person? So that is why, I would think it will be a more intuitive if we only allow non-negativity weights. And that is why we add that constraint. It actually makes our optimization problem harder than the non-constraint version, the optimization problem without that particular constraint. We eventually manage to make it as an unconstrained concave maximization problem, but that revision is definitely more complicated. But I thought that was for intuition purpose. Peng, do you want to add anything to the discussant's comments?
No, I don't, but I'm answering the question in chat. You can continue.
Okay. And let me see. And I mean, for the exact balance thing, I totally agree with José. In this kind of in the nature of this kind of study, it's possible that we cannot achieve exact balance. And in that case, one thing I can think of is that due to this kind of effect hierarchy relationship, we can say, okay, we're going to enforce more balance to the more important effects, say the lower order interactions. And for the relatively higher order interactions that are still non-negligible, we can add some tolerances for the balances. Yes, that's all. Some of my thoughts.
Okay, I think this is a good point to thank Ruoqi for the nice talk and Luke and José for their good contribution to our seminar this week. So let me introduce our speaker for next week, Ricardo Silva from UCL, and he will talk about intervention generalization, a view from factor graph models. Okay. So that marks the end of this seminar.